The telescope dome opens at sunset. Metal groans against metal, a circular aperture widening to reveal darkening sky. Inside, the primary mirror weighs 8 meters of glass coated in aluminum, polished to within 30 nanometers of perfect curvature. The observatory computer begins its nightly routine pointing calibration. Atmospheric correction tables. Target list downloaded from mission control 3 time zones away. By the time true darkness arrives, the telescope is already tracking, compensating for Earth's rotation at 15 degrees per hour. Holding distant galaxies motionless in its field of view, only took 4 billion years for matter to arrange itself into instruments capable of measuring its own arrangement. Tonight's targets include a galaxy cluster at redshift z equals 1.4, meaning the photons now entering the detector left their source 9 billion years ago, when Earth was a disk of undifferentiated dust and the Sun had not yet ignited. The exposure begins. Silicon pixels count incoming photons one by one, 300 electrons accumulating in a single detector well over the course of 20 minutes, building signal above the noise floor. The astronomer monitoring remotely from a campus office sees the image assemble line by line, a mosaic of gravitationally lensed arcs appearing against black. This particular observation is the 11th attempt to measure the same cluster. Each previous image revealed details that disagreed with predictions. Mass distributions calculated from gravitational lensing don't match mass distributions inferred from galaxy velocities, which don't match mass distributions derived from X-ray emission temperatures. 3 independent methods, 3 incompatible answers. The cluster contains dark matter. Certainly rotation curves and lensing geometry demand it, but the dark matter refuses to distribute itself according to the simulations. Real halos show cores where simulations predict cusps. Small satellite galaxies appear in different numbers than theory allows. The worst theory, in this case, is the one that works almost everywhere else. Astrophysics operates at the intersection of distance and time, where every observation arrives as historical document. Light travels at exactly 299,792,458 meters per second in vacuum, a speed that transforms astronomy into archaeology. The photon entering the detector at this moment left its source before vertebrates colonized land, before plants evolved roots, before oxygen concentrations in Earth's atmosphere stabilized above 10%. The universe visible tonight is younger than the universe that exists tonight, younger by precisely the light travel time. A delay that increases with distance until the most remote objects appear as they were shortly after the Big Bang. Their starlight stretched into infrared by 13.8 billion years of cosmic expansion. Dry irony accumulates in the data archive the farther we look. The younger things get. The telescope pivots 3 degrees eastward, hydraulics whispering through steel. Next target, a star system 41 light-years distant. A K-type dwarf with 2 confirmed planets detected via radial velocity method. The star wobbles. Its spectrum shifts absorption lines sliding blueward when an orbiting planet pulls the star toward Earth, then redward as the planet swings behind and pulls the star away. The wobble amplitude reveals planetary mass. The wobble period reveals orbital distance. Together they suggest a super-Earth in the habitable zone, a world 1.6 times Earth's radius orbiting well within the region where liquid water could persist on a rocky surface. But radius and mass give density, and density reveals composition. This particular world, despite its promising orbit, possesses a density of 3.1 grams per cubic centimetre, too low for pure rock, too high for pure water. The planet is neither Earth twin nor ocean world, but something in between, a category with no representative in our own solar system. Atmosphere unknown, surface conditions undetermined, biosignatures undetectable at current instrument sensitivity. The telescope can confirm the planet exists, and measure its mass and orbit with precision sufficient to schedule observations a century from now. It cannot determine whether anything lives there. The observation completes. Data streams to archive servers in 3 countries simultaneously. Redundant storage protecting against disk failure and institutional collapse. Within 6 months, 12 independent research groups will analyze the same photons, each arriving at slightly different conclusions depending on which systematic errors they choose to model and which they choose to ignore. The planet's mass will be reported as 4.2 Earth masses plus or minus 0.7, an uncertainty range that includes or excludes volatile-rich compositions depending on assumptions about stellar activity and instrumental drift. Science advances through revision, not revelation. The dome remains open. Wind enters at 7 meters per second, creating microturbulence that degrades image quality by 0.3 arc-seconds measurable, correctable, unavoidable. Adaptive optics compensate in real time, deforming a small mirror at 1000 Hz to counteract atmospheric distortion. The corrected image sharpens. Stars that appeared as blurred disks resolve into points. But the correction is imperfect. Turbulence occurs on scales smaller than the wavefront sensor can detect, and some distortion always remains embedded in the data. A reminder that clarity is relative and observation is negotiation between instrument and atmosphere. The night proceeds in exposures. Photons accumulate. Electrons migrate through silicon lattices. Cosmic rays strike the detector 60 times per hour, creating bright streaks that must be identified and masked in post-processing. Satellite trails cross the field Starlink. OneWeb. Classified military hardware, each adding a linear artifact that ruins the exposure for science but provides precise astrometric calibration. Even interference contains information, if interpreted correctly. By dawn, the telescope has observed 17 targets across 8 wavebands, accumulating 400 gigabytes of raw data. The dome closes. Mirrors are covered with protective aluminum blankets. Instruments enter safe mode, awaiting the next sunset. Somewhere in the desert, under brightening sky, matter rests after a night spent measuring matter. The observations will take months to calibrate, years to interpret fully, and decades to reconcile with theory. Some will be cited in textbooks. Others will vanish into archives, retrieved only when new missions render old data relevant again. The universe does not wait for analysis. It continues expanding, cooling, rearranging itself according to rules we approximate with mathematics and test with glass. Theories grow with each new image, not stronger, not simpler, but more entangled, more dependent on parameters we cannot measure directly, more aware of their own incompleteness. Only the photons remain indifferent. The history of spectroscopy begins with sunlight and a prism. 1666. Isaac Newton darkens a room, admits a single beam through a shutter, watches white light separate into component colours projected against the wall. Red, orange, yellow, green, blue. Violet, a continuous spectrum revealing that white contains multitudes. The observation is purely optical, a demonstration of refraction, angles measured with precision but interpreted as geometry rather than chemistry. Light bends because different wavelengths propagate at different speeds through glass. Nothing about the rainbow suggests atoms or elements or the composition of stars. 148 years pass before Joseph von Fraunhofer notices the dark lines. 1814, a German optician grinding lenses for telescopes examines solar spectrum with instruments refined beyond Newton's capability. The rainbow is no longer continuous. Hundreds of thin black lines interrupt the color's absorption features at specific wavelengths, always appearing in the same positions regardless of prism orientation or atmospheric conditions. Fraunhofer catalogues 574 lines, labels the strongest with letters the D lines in yellow, the H and K lines in violet, and publishes tables giving their wavelengths to within half a nanometer. He does not know what causes them. He suspects the lines originate in the Sun rather than Earth's atmosphere because stellar spectra show similar patterns, though the relative intensities differ from star to star. The dark lines are messages written in a language not yet invented. Gustav Kirchhoff and Robert Bunsen decode the syntax in 1859. They heat elements in a flame sodium, potassium, calcium, iron and pass the emitted light through a spectroscope. Each element produces a unique pattern of bright emission lines at precisely the same wavelengths where Fraunhofer's dark absorption lines appear in sunlight. The interpretation assembles quickly. The Sun's hot interior emits continuous spectrum, but cooler gas in the solar atmosphere absorbs specific wavelengths corresponding to atomic transitions in that gas. Spectroscopy becomes chemical analysis at astronomical distance. Within a decade, researchers identify sodium, magnesium, calcium, chromium, iron, nickel, copper, and zinc in the Sun without ever touching solar material. Dry irony, we learned the Sun's composition before we understood our own ocean floor, but some lines refuse identification. The most prominent appears in the yellow-green during solar eclipses, a bright emission feature at 587.5 nanometers that matches no known element in any laboratory on Earth. Norman Lockyer observes the line during the 1868 eclipse and proposes a new element, naming it helium after Helios, the Greek sun god. The suggestion is considered speculative, possibly embarrassing. Elements are discovered in minerals and solutions, not inferred from coloured light arriving from objects 93 million miles distant. Helium remains hypothetical for 27 years until William Ramsay isolates it from uranium ore in 1895, heating cleveite and capturing the released gas. The terrestrial sample spectrum matches the solar line exactly, wavelength agreement to within experimental error. The Sun knew about helium first. Spectroscopy expands beyond visible light. By 1900, photographic plates sensitive to ultraviolet reveal additional absorption features invisible to human eyes. Infrared detectors, still primitive, hint at molecular bands absorption patterns caused by vibrating and rotating molecules rather than atomic transitions. Water vapor, carbon dioxide, methane. Each molecule absorbs infrared at characteristic frequencies determined by bond lengths and atomic masses. Planetary atmospheres become legible from spectra alone. Compositions inferred without direct sampling, yet mysteries accumulate faster than solutions. Stellar spectra show patterns that require increasingly elaborate explanations. Some stars display broad, shallow absorption lines indicating rapid rotation, Doppler broadening from gas moving toward and away from the observer simultaneously. Others show sharp lines split into pairs or triplets, suggesting magnetic fields strong enough to alter atomic energy levels via the Zeeman effect. A few rare spectra contain emission lines superimposed on absorption features, implying shells of hot gas surrounding cooler photospheres, geometries that violate simple models of stellar structure. The worst stars are the ones that don't fit the sequence. Annie Jump Cannon at Harvard College Observatory catalogues 350,000 stellar spectra between 1896 and 1940, developing the classification system still used today. B, A, F, G, K, M, a sequence ordered by surface temperature, running from 40,000 Kelvin for the hottest O-type stars to 2,500 Kelvin for the coolest M-dwarfs. The sequence is empirical, derived from pattern recognition rather than theory. Cannon memorizes spectral features, sorting photographic plates by eye at a rate of 3 spectra per minute, her decisions forming the foundation of 20th century stellar astrophysics. Only later does quantum mechanics explain why the sequence exists, why hydrogen lines strengthen through A and F before fading, why helium appears only in hot stars, why titanium oxide bands emerge in the coolest spectra. Classification precedes understanding by decades, always. In 1913, Niels Bohr proposes that electrons orbit atomic nuclei in quantized energy levels. jumping between levels by absorbing or emitting photons with energies exactly equal to the difference between states. The model explains hydrogen's spectrum perfectly: the Balmer series in visible light, the Lyman series in ultraviolet, the Paschen series in infrared, all predicted by a single equation relating wavelength to integers. But helium requires modification. Lithium requires further adjustment. By the time spectroscopists reach iron with its 26 electrons, the calculations become intractable without approximations. Every element complicates the theory that explained the previous element. Spectroscopy reveals cosmic motions. Doppler shifts wavelength changes caused by relative velocity between source and observer allow measurement of stellar rotation, binary orbital speeds, galactic rotation curves, and the expansion of the universe itself. A spectral line at 500 nanometers in the laboratory appears at 500.5 nanometers in the spectrum of a receding galaxy, the shift indicating velocity of 300 kilometers per second directly away from Earth. The technique works equally well for approaching objects. Blue shifted lines indicate motion toward the observer. Between 1912 and 1925, Vesto Slipher measures radial velocities for 41 galaxies, finding that most are receding, the first observational evidence for cosmic expansion, though the interpretation awaits Edwin Hubble's distance measurements. Galaxies flee before we finish naming them. Forbidden lines appear in nebula spectra emission features at wavelengths that should not exist according to laboratory quantum mechanics. The strongest glowing green in planetary nebulae and supernova remnants sits at 500.7 nanometers and resists identification for decades. Astronomers initially attribute it to an unknown element called nebulium, repeating the helium naming pattern. But Ira Bowen demonstrates in 1927 that the lines arise from doubly ionized oxygen in extremely low-density gas conditions impossible to replicate in terrestrial laboratories, where collisions de-excite atoms before they can emit forbidden line photons. The forbidden transitions occur readily in space, where particle densities drop below 1 per cubic centimeter and atoms remain undisturbed for hours between collisions. Space provides experimental conditions unavailable on Earth. Modern spectrographs disperse light across thousands of spectral channels simultaneously, recording flux at each wavelength with photon-counting precision. Echelle spectrographs cross-disperse light into two-dimensional arrays, achieving resolving powers above 100,000 sufficient to detect radial velocity changes of 1 meter per second, the wobble induced by an Earth-mass planet orbiting a sun-like star at 1 astronomical unit. High-resolution spectroscopy reveals stellar surface features, star spots causing periodic line profile variations, convective granulation creating asymmetric line shapes, differential rotation making equatorial regions spin faster than polar regions. Stars are not smooth black bodies, but roiling surfaces of magnetized plasma. Absorption lines carry isotopic information. Deuterium-hydrogen with an added neutron absorbs at wavelengths shifted slightly from normal hydrogen due to its doubled mass. The shift amounts to 0.08 nanometers for the Lyman alpha line, barely detectable but measurable with sufficient instrumental stability. Primordial deuterium abundance tests, Big Bang nucleosynthesis. Models theory predicts that 3 minutes after the universe began, nuclear reactions produced 1 deuterium nucleus per 40,000 hydrogen nuclei, a ratio that decreases over cosmic time as deuterium fuses into heavier elements inside stars. Observations of distant gas clouds, their spectra preserved from earlier cosmic epochs, confirm the predicted ratio to within 10%, perhaps the most precise agreement between theory and observation across 13 billion years. Only took a century to check the first 3 minutes, yet discrepancies persist. Some stellar spectra show lithium abundance is 10 times lower than predicted by standard stellar evolution models. Others display carbon to oxygen ratios incompatible with known nuclear synthesis pathways. White dwarf atmospheres occasionally reveal metals that should have sunk below the photosphere within days, their presence indicating ongoing accretion from unseen debris disks or destroyed planets. Each anomaly demands explanation: convective mixing, atomic diffusion, mass transfer from binary companions, but explanations multiply faster than confirmations, leaving libraries of spectra annotated with question marks. The dark lines remain, carrying their quiet refusals. Henrietta Swan Leavitt sits at a desk in Harvard College Observatory, examining photographic plates taken from Arequipa, Peru. The year is 1908. Her assigned task involves measuring variable stars in the Small Magellanic Cloud, a satellite galaxy visible only from southern latitudes, its light requiring 8-hour exposures to register on glass coated with silver halide emulsion. Each plate captures the same field on different nights. Stars that appear bright on one plate may dim on another, their variability recorded as changing spot sizes on the developed image. Leavitt's job is to measure, catalogue, and report, not to interpret, though interpretation arrives unbidden. She notices a pattern in the Cepheid variables. Cepheids pulse with metronomic regularity, brightening and fading over periods ranging from 1 day to 100 days depending on the individual star. Classical Cepheids, named after Delta Cephei, the prototype discovered in 1784, vary by 1 to 2 magnitudes, their light curves asymmetric, rising to maximum brightness faster than they fade to minimum. The pulsation mechanism remains unknown in 1908. Eddington will not propose the Kappa mechanism opacity changes in ionized helium, driving expansion and contraction until 1917. Leavitt works without theory, measuring periods and magnitudes, entering numbers into ledgers. The Small Magellanic Cloud provides crucial experimental advantage: distance uniformity. All stars within the cloud lie approximately the same distance from Earth, roughly 160,000 light-years. Though this value remains undetermined in Leavitt's era, distance uniformity means apparent brightness reflects intrinsic luminosity directly, without the confounding variable of unknown distances that plague studies of Milky Way stars. Leavitt measures 17 Cepheids initially, then 25, comparing their periods to their apparent magnitudes. The correlation emerges cleanly: longer period Cepheids appear brighter. Period determines luminosity. She publishes in 1912. The paper runs 4 pages and contains 1 table. The period luminosity relation transforms Cepheids into standard candles distance indicators, whose intrinsic brightness can be inferred from their pulsation period. Observe a Cepheid, measure its period, calculate its luminosity from Leavitt's relation. Compare luminosity to apparent brightness, solve for distance. The method works across millions of parsecs, extending the cosmic distance ladder far beyond parallax measurements that fail beyond a few hundred light-years. By 1923, Edwin Hubble uses Cepheids in the Andromeda Nebula to prove it lies outside the Milky Way, a separate galaxy at distance 800,000 light-years, a value later revised upward to 2.5 million light-years as Cepheid calibration improves. Only took 14 years to double the known universe. But the relation scatters. Not every Cepheid of a given period has identical luminosity. Metallicity affects pulsation stars with higher abundances of elements heavier than helium are slightly dimmer than metal-poor stars of the same period. The effect amounts to 0.2 magnitudes per dex of metallicity difference, small but systematic, introducing distance errors of 10% if uncorrected. Worse. 2 distinct Cepheid populations exist: classical Cepheids, young massive stars found in spiral arms and star-forming regions, and Type II Cepheids, older lower mass stars inhabiting globular clusters and galactic halos. Type II Cepheids are fainter by 1.6 magnitudes at a given period, making distance estimates wrong by a factor of 2 if populations are confused. Standard candles require standardization of the standards. Walter Baade identifies the two populations in 1952 while observing Andromeda with the newly completed Palomar 5-meter telescope. The resolution reveals individual Cepheids in Andromeda's halo that are fainter than their counterparts in spiral arms, despite similar periods. Baade recalibrates the distance scale, doubling distances to external galaxies and resolving long-standing tensions in the ages of globular clusters, which had appeared younger than the expansion age of the universe itself, a logical impossibility. The revision propagates through cosmology. A universe twice as large expands at half the rate, giving Hubble's constant a value of 250 kilometers per second per megaparsec rather than 500, later refined downward to 70 through improved calibrations. Each calibration requires recalibration decades later. Modern Cepheid observations use infrared rather than optical wavelengths. Dust in the interstellar medium absorbs and scatters blue light more efficiently than red, causing stars to appear dimmer and redder than they truly are. Extinction that varies unpredictably along different lines of sight. Infrared observations reduce extinction corrections by a factor of 10, though they cannot eliminate the effect entirely. The Spitzer Space Telescope measured Cepheid light curves at 3.6 microns, obtaining period luminosity relations with scatter reduced to 0.1 magnitudes. The James Webb Space Telescope, operating at wavelengths up to 28 microns, pushes Cepheid distances beyond 30 megaparsecs, approaching velocities where cosmic expansion becomes the dominant redshift source. Distance measurements become cosmology at sufficient remove. Parallax provides the zero-point calibration to convert Leavitt's relative period luminosity relation into absolute distances. Astronomers must measure the distance to at least one nearby Cepheid via geometric methods. Hipparcos satellite measured parallaxes for several hundred Cepheids in the 1990s, achieving uncertainties near 1 milliarc-second sufficient for stars within a few hundred parsecs, but inadequate for precise calibration. Gaia mission improves parallax precision by 2 orders of magnitude, reaching uncertainties below 10 microarc-seconds for bright stars and enabling direct distance measurements to Cepheids beyond 2 kiloparsecs. The Gaia DR3 catalogue, released 2022, contains parallaxes for over 300 Cepheids, refining the period luminosity zero point to within 3%. 3% uncertainty propagates into every extragalactic distance. Yet some Cepheids pulsate in multiple modes simultaneously, beating between periods, creating amplitude modulation on timescales of decades. Others show erratic period changes, abrupt jumps, or slow drifts unexplained by steady stellar evolution. A few display the Blaschko effect, their light curves changing shape from cycle to cycle in patterns that repeat over tens to hundreds of pulsations. Each anomaly suggests physics beyond the standard Kappa mechanism magnetic fields, rotation, convective overshoot, or mode coupling effects too subtle to model reliably. Even the standard candles flicker irregularly. Henrietta Leavitt died in 1921, before the full cosmological implications of her work became clear. She published little beyond catalogues of variable star periods and magnitudes. No Nobel Prize was awarded. The prize is not given posthumously, and Leavitt's work was seen as observational rather than theoretical. Gösta Mittag-Leffler nominated her in 1924, unaware she had died 3 years earlier. The period luminosity relation carries her name in some textbooks but not others. The pattern persists, observation precedes recognition. Cataloguing precedes interpretation. Measurement outlasts the measurer. The Cepheids continue pulsing, indifferent to calibration disputes. Edwin Hubble stands before the 100-inch Hooker telescope on Mount Wilson, California, preparing photographic plates for a night's work. The year is 1923. His target, the Andromeda Nebula, a faint smudge visible to naked eyes on autumn nights, appearing in medieval star catalogues as a small cloud, debated for centuries as either a nebulous region within our galaxy or an island universe beyond it. Previous observers have noted spiral structure, bright knots that might be star clusters, and occasional novae-stellar explosions that briefly outshine their surroundings before fading. Heber Curtis argued in 1920 that the nebulae are external galaxies based on their nova rates and rotational velocities. Harlow Shapley countered that they must lie within the Milky Way, else the universe would be inconceivably vast. The telescope resolves individual stars in Andromeda's outer regions. Hubble identifies Cepheid variables 9 initially, then 12, then 36 over subsequent observing seasons. He measures their periods 5 days, 10 days, 31 days. Applying Leavitt's period luminosity relation, he calculates luminosities, compares to apparent brightnesses, derives distance, the result 900,000 light-years, a value later revised to 2.5 million light-years after Bard's population corrections. Andromeda is not a nebula but a galaxy, comparable in size to the Milky Way, containing hundreds of billions of stars, lying at a distance that places it entirely outside our own stellar system. The observable universe expands from one galaxy to many in a single publication. Space becomes plural overnight. Between 1923 and 1929, Hubble extends distance measurements to 18 galaxies using Cepheids, and to dozens more using brightest stars as crude distance indicators. Meanwhile, Vesto Slipher's spectroscopic observations accumulate 41 galaxy spectra showing predominantly red-shifted absorption lines, indicating recession velocities ranging from 100 to 1,000 kilometers per second. Hubble plots velocity against distance. The correlation appears linear. More distant galaxies recede faster, with velocity proportional to distance. The slope of the relation 500 km per second per megaparsec in Hubble's initial estimate becomes known as Hubble's constant. Though it is neither constant across cosmic time nor accurately measured in Hubble's era, the universe expands. Apparently, general relativity predicts expansion. Alexander Friedmann derives expanding universe solutions to Einstein's field equations in 1922, finding that space itself can stretch, carrying galaxies apart without requiring them to move through space. Georges Lemaitre independently obtains similar solutions in 1927 and proposes that recession velocity should increase with distance, the Hubble law, before Hubble publishes it. Einstein initially resists, having introduced a cosmological constant specifically to maintain static universe solutions, but abandons the constant after Hubble's observations demonstrate cosmic expansion. Later, Einstein reportedly calls the cosmological constant his biggest blunder, though the quote's authenticity remains disputed, and the constant returns to cosmology in the 1990s as dark energy. Dry irony, the blunder becomes Nobel-worthy 70 years later. Hubble's distance estimates are systematically wrong. His Cepheids include both classical and Type II populations, unrecognized as distinct until Bard's work. His brightest star method assumes all galaxies contain stars of similar maximum luminosity, an assumption valid statistically but poor for individual cases. His photographic photometry suffers from emulsion nonlinearity, atmospheric extinction uncertainties, and extinction from interstellar dust within the Milky Way corrections applied inconsistently or not at all. When Bard recalibrates distances in 1952, Hubble's constant drops from 500 to 250, doubling the size and age of the universe. Further refinements through the 1970s and 80s push the value below 100, then settle near 70 by the late 1990s. Each generation revises the previous generation's precision. The Hubble Space Telescope Key Project dedicates 8 years, 1994 through 2001, to measuring Hubble's constant using multiple distance indicators. Cepheids, Type Ia supernovae, Tully-Fisher relation for spiral galaxies, surface brightness fluctuations in ellipticals. The team observed Cepheids in 31 galaxies out to 20 megaparsecs, establishing a local distance ladder anchored by geometric parallaxes from Hipparcos. The result 72 kilometers per second per megaparsec, plus or minus 8 roughly 10% uncertainty, representing a factor of 10 improvement over estimates from 2 decades prior. 10% uncertainty seems adequate until other methods achieve 5%. Cosmic microwave background measurements offer an independent route. The Planck satellite maps temperature fluctuations in the relic radiation from 380,000 years after the Big Bang, when the universe cooled sufficiently for protons and electrons to combine into neutral hydrogen, allowing photons to stream freely. The fluctuation pattern peaks in the angular power spectrum at specific multipole moments, encodes information about cosmic geometry, matter density, and expansion history. Fitting a standard cosmological model to Planck, data yields Hubble's constant of 67.4 km per second per megaparsec, with uncertainty below 1%. The precision surpasses local measurements by a factor of 10, but the values disagree by 5 sigma. Planck gives 67.4. Hubble Space Telescope Cepheids plus Type Ia supernovae gives 73. The discrepancy persists across multiple independent analyses using different supernova samples, different Cepheid calibrations, different statistical methods, SH0ES collaboration, supernova H0 for the equation of state, refines local measurements to 1.04% uncertainty, using more than 2,000 Cepheids observed with HST and more than 1,000 Type Ia supernovae. The value remains 73.04. in 5.6 sigma tension with Planck. Carnegie-Chicago Hubble program uses an entirely different distance ladder based on tip-of-the red giant branch stars rather than Cepheids, obtaining 69.8 between the two extremes, but agreeing fully with neither. Precision generates crisis when measurements diverge. Systematic errors are the obvious suspect. Perhaps Cepheid period luminosity relations contain metallicity, dependencies stronger than assumed. Perhaps Type Ia supernovae evolve with cosmic time, becoming intrinsically brighter or dimmer at different epochs. Perhaps Milky Way dust extinction corrections are wrong, or peculiar velocities in the local universe mimic faster expansion, or photometric calibration drifts between instruments. Each possibility has been investigated. Metallicity corrections have been measured in multiple galaxies at multiple wavelengths. Supernova evolution has been constrained by splitting samples by host galaxy properties. Dust corrections have been tested using infrared observations where extinction is minimized. The tension remains. Gravitational wave standard sirens offer a third path. When two neutron stars or black holes merge, they emit gravitational waves whose amplitude and frequency evolution encode the source's luminosity distance. If the merger produces electromagnetic counterparts, gamma-ray bursts, kilonovae allowing redshift measurement, then distance and redshift together determine Hubble's constant without requiring distance ladders or cosmic microwave background modelling. The first such measurement, from neutron star merger GW170817, gave 70 km per second per megaparsec with 14% uncertainty consistent with both Planck and local measurements due to large error bars. As gravitational wave detectors improve and merger catalogues grow, this method will achieve few percent precision independent of all other approaches. Only took a century after Hubble to invent entirely new measurement techniques. The Hubble tension may indicate new physics, sterile neutrinos, decaying dark matter, modified gravity, or effects not yet imagined, or it may indicate unrecognized systematic errors in Cepheid photometry, supernova standardization, or Planck foreground subtraction. or both measurements are correct and tension arises from comparing local expansion rate averaged over the past few billion years within our cosmic neighbourhood to global expansion rate inferred from early universe conditions propagated forward 13.8 billion years. Space expands non-uniformly in the presence of density inhomogeneities, and local voids or overdensities could create percent-level differences between local and cosmic mean expansion rates. Dry observation, we can measure Hubble's constant better than we understand it. The value remains under investigation. James Webb Space Telescope extends Cepheid observations to unprecedented distances and infrared wavelengths. Gaia's astrometry refines parallax-based calibrations. Euclid and Vera Rubin Observatory will discover tens of thousands of new Type Ia supernovae, multiplying sample sizes and constraining systematics through sheer statistical power. The tension may resolve, or deepen, or fragment as different methods subdivide into variants yielding slightly different values. The universe expands at the rate it expands. We measure, recalibrate, debate. Galaxy rotation curves should decline. Newtonian mechanics predicts that orbital velocity decreases with distance from a gravitational centre. Following the inverse square law, once most mass lies interior to the orbit. Planets in the solar system obey this pattern. Mercury orbits at 48 kilometers per second, Earth at 30, Neptune at 5.4. Beyond Neptune, in the Kuiper belt, orbital velocities drop further still. Dwarf planet Eris circles the Sun at 3.4 kilometers per second at a distance of 96 astronomical units. The pattern holds across 6 orders of magnitude in orbital radius. Mass concentrates near the centre, velocity falls with distance. Spiral galaxies refuse to cooperate. Vera Rubin begins measuring galaxy rotation curves in the 1970s using optical spectroscopy at Kitt Peak National Observatory and Carnegie Institution. Her method observes emission lines from ionized hydrogen in galaxy disks, measure Doppler shifts on both approaching and receding sides, convert wavelength shifts to rotational velocities, plot velocity versus distance from galactic center. For nearby spiral galaxy NGC 3198 optical observations extend to 30 kiloparsecs from the nucleus, far beyond the visible stellar disk where most luminous matter concentrates. Newtonian prediction velocity should decline beyond the bright disk, dropping towards zero in the outer regions where star density fades to background. The velocity remains constant at 200 kilometers per second out to the last measured point. Rubin's observations are not the first. Horace Babcock measured rotation of Andromeda in 1939, finding similar flat curves but attributing them to measurement error or unknown systematic effects. Janort noted discrepancies between dynamical mass estimates and luminous mass in the 1940s. Fritz Zwicky calculated masses of galaxy clusters in the 1930s using velocity dispersions, finding cluster masses hundreds of times larger than expected from visible galaxies, evidence he termed dunkel Materie, dark matter. But Zwicky's cluster results could be explained by hot intracluster gas, undetected at the time. Rotation curves provide cleaner tests, individual galaxies, circular orbits, minimal assumptions about equilibrium or projection effects. By 1980, flat rotation curves are confirmed in more than 60 spiral galaxies across a range of luminosities, sizes, and morphologies. Radio observations of neutral hydrogen extend measurements far beyond optical limits out to 50 kiloparsecs, 80 kiloparsecs, in some cases beyond 100 kiloparsecs where galaxy disks fade to invisibility, but hydrogen emission remains detectable. Every galaxy shows the same pattern. Velocity rises in the inner regions where stars dominate, then flattens in the outer regions rather than declining. The flatness implies mass continues increasing linearly with radius even where no stars shine. Dry irony galaxies are mostly made of something we cannot see. The missing mass must be dark, emitting no light across the electromagnetic spectrum. detectable only through gravitational effects. If rotation curves remain flat to radius r, then enclosed mass must grow as m proportional to r rather than remaining constant beyond the stellar disk. This implies dark matter halos extending 10 times farther than visible galaxies, with total masses 5 to 10 times larger than all stars and gas combined. The halos are roughly spherical, based on modelling of rotation curves and velocity dispersions. They persist across cosmic time. High redshift galaxies observed at look-back times of 10 billion years also show flat rotation curves, indicating dark matter dominated galaxy masses even in the early universe. The composition remains unknown after 50 years of searching. Direct detection experiments attempt to observe dark matter particles interacting with ordinary matter in laboratory detectors. The leading candidate, weakly interacting massive particles, or WIMPs, should scatter occasionally off atomic nuclei, depositing energy detectable as phonons, ionization or scintillation light. Experiments employ tons of ultrapure materials, liquid xenon, germanium crystals, argon-shielded deep underground to reduce cosmic ray backgrounds, cooled to cryogenic temperatures to minimize thermal noise, monitored for recoil events consistent with dark matter collisions. Decades of searching have yielded only null results and ever-tightening exclusion limits. They have not been detected. Axions provide an alternative, proposed originally to solve the strong CP problem in quantum chromodynamics. Axions are ultralight bosons with masses below 1 millielectron volt, millions of times lighter than electrons. If axions compose dark matter, they behave as wave-like fields rather than particle-like objects, forming coherent states with macroscopic quantum properties. Axion haloscopes search for axion to photon conversion in strong magnetic fields, scanning through possible masses by tuning resonant cavities. The axion dark matter experiment has excluded certain mass ranges but requires decades to scan the full, theoretically motivated parameter space. Or perhaps dark matter does not exist, and gravity requires modification at galactic scales. Modified Newtonian dynamics proposes that gravitational acceleration deviates from inverse square law below a critical threshold, approximately the acceleration scale observed in galaxy outskirts. The theory successfully reproduces flat rotation curves without invoking dark matter, using a single empirical parameter. It also predicts a tight correlation between galactic luminosity and rotation velocity, the Tully-Fisher relation, which emerges naturally but requires fine-tuning in dark matter models. But modified Newtonian dynamics fails on larger scales. Galaxy cluster masses inferred exceed cluster masses from hot gas temperatures and gravitational lensing, requiring additional dark matter even within modified gravity. Cosmic microwave background fluctuations cannot be explained. The acoustic peak positions depend on dark matter density, decoupling from baryonic matter at recombination. Bullet cluster observations show gravitational lensing mass peaks offset from X-ray emission peaks, indicating dark matter passing through collision while baryonic gas experiences ram pressure and lags behind. Dry observation modifying gravity solves one problem while creating 3 others. No model is entirely satisfactory. Cold dark matter requires baryonic physics to explain small-scale structure. Modified gravity requires dark matter to explain large scales. Self-interacting and warm dark matter require interactions or masses not predicted by particle physics. Each theory has successes. Each has failures. Each has advocates who emphasize the former and minimize the latter. The rotation curves that revealed the problem in 1970 still lack definitive explanation in 2025. Despite thousands of papers and multiple dedicated experiments, dark matter, if it exists, comprises 85% of matter in the universe, yet interacts only gravitationally with the remaining 15%. This asymmetry overwhelming abundance coupled with minimal interaction challenges intuition. Why should the dominant component be invisible? Why should baryonic matter, rare in cosmic census, be the only kind that forms stars, planets, and observers? The anthropic answer, only baryonic matter can cool efficiently, radiating energy via electromagnetic processes, collapsing into dense structures, forming complexity. Dark matter remains diffuse, its halos providing gravitational scaffolding for galaxy formation but never condensing into discrete objects themselves. Galaxies spin within invisible cages we detect only through their captivity. The cosmic microwave background arrives from all directions simultaneously. It fills the sky uniformly, no gaps, no shadows, no regions where ancient light fails to reach. The radiation originates from 380,000 years after the Big Bang, the moment when the universe cooled below 3000 Kelvin and electrons combined with protons to form neutral hydrogen. Before recombination, photons scattered constantly off free electrons, trapped in an opaque plasma. After recombination, photons streamed freely through transparent space, their wavelengths stretching with cosmic expansion for 13.8 billion years until captured by radio telescopes and satellite detectors. The temperature is 2.725 Kelvin averaged across the entire sky, but the average conceals structure. Subtract the mean temperature and residual fluctuations appear hotspots and cold spots varying by tens of microkelvin, 1 part in 100,000 relative to the background. The Cosmic Background Explorer satellite maps these fluctuations in 1992 with 7-degree angular resolution, revealing patches of slightly warmer and slightly cooler radiation distributed across the celestial sphere. The pattern is neither random nor artificial. It represents density variations. In the early universe, regions slightly denser than average appear warmer. Regions slightly less dense appear cooler. The temperature differences encoding information about primordial quantum fluctuations, amplified by inflation and shaped by gravitational dynamics during the first few 100,000 years. Only took 13.8 billion years for those photons to arrive at our detectors. The Wilkinson microwave anisotropy probe improves angular resolution to 0.2 degrees, launched in 2001 and operating for 9 years. The temperature map sharpens. Individual acoustic peaks become visible. The pattern of hot and cold spots arranges itself according to physics of sound waves propagating through the primordial plasma. Before recombination, baryonic matter and photons were tightly coupled, pressure and gravity competing in oscillating modes, regions compressed by gravity heated up, photon pressure pushed back, creating expansion. Gravity pulled again, establishing standing wave patterns at specific wavelengths determined by the speed of sound in the plasma and the horizon size at recombination. These sound waves fossilize as temperature fluctuations in the cosmic microwave background. The angular power spectrum quantifies the pattern. Transform the temperature map into spherical harmonics mathematical functions describing patterns on a sphere, and calculate the power in each multipole moment. The power spectrum shows peaks at specific multipoles. First peak at L equals 220, second peak at L equals 540, third peak at L equals 800. The peak positions depend on cosmic geometry, matter density, baryon density, and dark energy content. Measure the peaks in for the cosmological parameters. Planck's satellite achieves this with unprecedented precision, operating from 2009 through 2013. Angular resolution reaches 5 arc-minutes. Frequency coverage spans 9 bands from 30 GHz to 850 GHz. Allowing separation of cosmic microwave background signal from foreground contamination synchrotron emission from our galaxy. Thermal dust. Free radiation from ionized gas. The resulting temperature map contains 50 million pixels, each with measured temperature and polarization. The angular power spectrum extends to multipole L equals 2500, revealing 6 acoustic peaks with sub% statistical uncertainties. The fit to standard cosmology is disturbingly good. 6 free parameters describe the lambda CDM model baryon density. cold dark matter density, cosmological constant, scalar spectral index of primordial fluctuations, optical depth to reionization, and amplitude of fluctuations. Planck constrains these parameters to percent level precision or better. Baryon density 0.0493 plus or minus 0.0002 times critical density. Cold dark matter density 0.265 plus or minus 0.004. The universe is spatially flat to within 0.4%. Dark energy comprises 68% of total energy density. Ordinary matter comprises 5%. Dark matter comprises 27%. Dry irony. We know the universe's composition to 3 significant figures, but not what most of it is. Polarization adds another layer. Photons scattered during recombination acquire preferential orientations. Linear polarization patterns encoding information about velocity fields in the primordial plasma and gravitational waves from inflation. 2 polarization modes exist: E mode, gradient-like patterns symmetric under parity, and B mode, Kerr-like patterns antisymmetric under parity. E mode polarization is detected robustly, its angular power spectrum agreeing with predictions from scalar density fluctuations. B mode polarization at large angular scales would indicate primordial gravitational waves, providing direct evidence for cosmic inflation and constraining the energy scale of inflation. B mode detection remains elusive at cosmological scales. The BICEP-2 experiment announces B mode detection in 2014, measuring polarization at degree angular scales from the South Pole. The signal appears consistent with gravitational waves from inflation with tensor to scalar ratio R equals 0.2. But subsequent analysis by Planck combining multiple frequencies reveals that galactic dust emits polarized thermal radiation at levels sufficient to explain the BICEP-2 signal. The gravitational wave detection evaporates into foreground contamination. Current upper limits place R below 0.036, constraining but not ruling out inflationary models. The universe remains quiet about its first moments. Yet small-scale anomalies persist. The cosmic microwave background appears slightly colder than expected at the largest angular scales, the missing power at low multipoles. The hemispheres are asymmetric. One half of the sky shows slightly larger fluctuations than the other. A dipole pattern inconsistent with statistical isotropy. A cold spot in the southern celestial hemisphere spans 10 degrees. Appearing unlikely in standard simulations but not impossible. These features could indicate new physics non-Gaussianity from exotic inflation models. Topology of space different from simple flat geometry, or interactions between matter and radiation beyond a standard model. Or they could be statistical flukes, unlikely but inevitable given that we observe only one universe. Foreground subtraction introduces systematic uncertainties. The Milky Way emits across all frequencies measured by cosmic microwave background experiments. Synchrotron radiation dominates below 70 GHz. Dust emission dominates above 100 GHz. Each component has distinct spatial and spectral properties, allowing separation by fitting multi-frequency maps to physical templates. But the separation is imperfect. Dust properties vary across the sky temperature. Opacity, grain composition. Residual foreground contamination remains in the cleaned maps, introducing percent-level uncertainties in derived parameters. Precision comes with caveats. The cosmological parameters inferred from Planck assume standard physics general relativity, adiabatic initial conditions, no exotic particle species beyond 3 neutrino flavors. Relaxing these assumptions changes parameter estimates. Allowing additional relativistic species increases Hubble constant by several percent. Allowing spatial curvature shifts matter density. Each modification adds free parameters. Improving fits to data at the cost of predictive power. Bayesian model comparison generally favors the simplest lambda CDM model, but the preference is statistical rather than definitive. The standard model works until it doesn't, somewhere in the tails of the distribution. The first exoplanet orbiting a Sun-like star is detected in 1995. Michel Mayor and Didier Queloz observe 51 Pegasi, a G-type dwarf 41 light-years distant in the constellation Pegasus, using radial velocity spectroscopy at the Haute-Provence Observatory. The star's spectrum shifts periodically blue-shifted, then red-shifted, then blue-shifted again, indicating orbital motion induced by an unseen companion. The period is 4.2 days. The velocity amplitude is 57 meters per second. These measurements imply a planet with minimum mass 0.47 times Jupiter's mass, orbiting at 0.05 astronomical units from its host star closer than Mercury to the Sun, completing an orbit in less than a week. The discovery violates expectations. Planet formation theory, developed from study of our solar system, predicts that giant planets form beyond the frost line, the distance from a star where temperatures drop below water's freezing point, allowing ice grains to condense and accrete into massive cores capable of capturing hydrogen and helium atmospheres. For Sun-like stars, the frost line lies near 3 astronomical units. Giant planets should orbit at Jupiter-like distances or beyond, taking years or decades to complete orbits. 51 Pegasi b orbits 20 times closer, experiencing stellar irradiation sufficient to heat its atmosphere above 1000 Kelvin. The planet should not exist where observations place it, yet it exists, and it is not alone. Within 5 years, astronomers discovered dozens of similar objects, hot Jupiters, gas giants orbiting within 0.1 astronomical units of their stars, with orbital periods measured in days rather than years. Some are more massive than Jupiter, others less, but all share the defining characteristic proximity to their host stars inconsistent with in situ formation. The planets must have formed farther out and migrated inward through interactions with the protoplanetary disk or through gravitational scattering by other planets. Migration timescales span millions of years. The process requires specific disk conditions, mass, viscosity, lifetime that vary from system to system, explaining why hot Jupiters appear in roughly 1% of Sun-like stars rather than all or none. Dry irony, our solar system becomes the exception rather than the template. Transit photometry revolutionizes detection. If a planet's orbit aligns such that it passes directly between star and observer, the planet blocks a fraction of starlight proportional to its cross-sectional area. For a Jupiter-sized planet transiting a Sun-like star, the brightness dip amounts to 1% lasting 2 to 4 hours, repeating each orbital period. The Kepler Space Telescope, launched 2009, monitors 150,000 stars continuously for 4 years, detecting transits with photometric precision of 20 parts per million. The mission discovers over 2,600 confirmed planets and an additional 2,200 candidates awaiting verification. The planets defy solar system categories. Super-Earths, planets with masses between Earth's and Neptune's. Radii between 1 and 4 Earth radii appear frequently in Kepler data despite having no representative in our system. Their compositions remain ambiguous. A planet twice Earth's radius could be a rocky world with thick hydrogen atmosphere, a water world with deep oceans above high-pressure ice layers, or something intermediate. Mass measurements from radial velocity follow-up provide density estimates, but density alone cannot uniquely determine composition. A planet with density 4 grams per cubic centimetre could be pure rock or half rock and half water, depending on internal structure and temperature. Mini-Neptunes occupy the gap between super-Earths and Neptune itself, planets with radii between 2 and 4 Earth radii, likely possessing substantial hydrogen-helium envelopes. They are the most common planet type in Kepler data, appearing around 30% of Sun-like stars, yet no analogue exists among solar system planets. Neptune's radius is 4 Earth radii, Uranus is slightly smaller. The solar system jumps from rocky planets at 1 Earth radius to ice giants at 4. skipping the 2 to 3 Earth radii range entirely. Only our planetary system lacks the universe's most common planet type. Atmospheric characterization proceeds slowly. Transmission spectroscopy observes starlight filtered through a planet's atmosphere during transit, comparing in-transit and out-of-transit spectra to measure wavelength-dependent absorption by atmospheric gases. Water vapor absorbs infrared at 1.4 microns, methane absorbs at 2.3 microns, carbon dioxide absorbs at 4.5 microns. Detection requires signal-to-noise ratios above 10, achievable only for large planets, hot Jupiters and warm Neptunes transiting bright stars. Smaller planets around fainter stars produce signals below detection thresholds for current instruments. The James Webb Space Telescope improves sensitivity by 2 orders of magnitude compared to Hubble, operating at infrared wavelengths from 0.6 to 28 microns with collecting area 6 times larger. Early observations detect carbon dioxide in the atmosphere of WASP 39b, a hot Jupiter transiting a G-type star, marking the first unambiguous detection of this molecule on an exoplanet. Subsequent observations reveal water, methane, sulfur dioxide chemical inventories indicating atmospheric dynamics, photochemistry and disequilibrium processes. Yet biosignatures remain beyond reach. Oxygen in Earth's atmosphere exists at 21% by volume, maintained far above equilibrium concentrations by photosynthetic life. Detecting comparable oxygen abundances in exoplanet atmospheres would require hundreds of transits observed at infrared wavelengths, where oxygen absorbs, accumulating signal over years of observation. Even then, oxygen alone is insufficient evidence for biology. Photodissociation of water vapor and carbon dioxide can produce abiotic oxygen in certain atmospheric conditions. Phosphine, methane, dimethyl sulfide. Each proposed biosignature gas suffers similar ambiguities. Context matters more than detection. TRAPPIST-1 system contains 7 Earth-sized planets orbiting an M-dwarf star 40 light-years distant. 3 planets designated E, F, and G orbit within the habitable zone, receiving stellar flux comparable to Venus, Earth, and Mars respectively. Transit timing variations reveal the planets gravitationally interact, constraining their masses and densities. Planets E, F, and G have densities consistent with rocky compositions, low enough to allow substantial water content, but high enough to exclude hydrogen envelopes. The system appears promising for habitability studies, but M-dwarfs emit powerful flares, sudden brightening events releasing energies equivalent to billions of hydrogen bombs, potentially stripping planetary atmospheres or sterilizing surfaces. Proximity to a star brings both warmth and violence. Occurrence rates quantify discovery biases. Transit surveys preferentially detect large planets on short-period orbits. Hot Jupiters transit frequently with deep signals, while Earth-sized planets in year-long orbits transit once per year with signals near noise limits. Correcting for detection biases yields intrinsic occurrence rates. Hot Jupiters around 1% of Sun-like stars. Warm Neptunes around 10%. Super-Earths and mini-Neptunes around 30 to 50%. Earth-sized planets in habitable zones appear around 10 to 20% of Sun-like stars, with uncertainties spanning factors of 2 due to small number statistics, extrapolating to the galaxy tens of billions of potentially habitable worlds. If habitable zone placement correlates with habitability, but no planet resembles Earth precisely. Every exoplanet orbits a different star hotter or cooler, more or less massive, metal-rich or metal-poor. Every planetary system has different architecture. Some contain multiple planets in compact configurations. Others show single giants on wide orbits. Still others display high eccentricities indicating violent dynamical histories. Earth is not a category but a point in high-dimensional parameter space, and we do not yet know which dimensions matter for life. The planets exist. Their atmospheres await reading. Their surfaces remain unimaged, hidden behind glare. Water ice on the Moon is confirmed in 2020 by the Stratospheric Observatory for Infrared Astronomy. Sophia, a Boeing 747 carrying a 2.7-metre telescope observing at altitudes above 99% of atmospheric water vapour. The instrument detects the 6.1 micron absorption feature of molecular water in sunlit regions near the lunar south pole. Specifically within Clavius crater, the concentration is low, 100 to 400 parts per million, equivalent to a 12-ounce bottle of water per cubic metre of regolith. Still, water exists where none should persist exposed to solar radiation, unshielded by atmosphere, in locations experiencing daytime temperatures above 100 Celsius. The Moon was supposed to be dry. Apollo samples returned between 1969 and 1972 contained no detectable water. Laboratory analysis found less than 1 part per billion in bulk rock samples, consistent with formation models that invoked a giant impact between proto-Earth and a Mars-sized body 4.5 billion years ago. The impact vaporized both colliding objects, ejecting material that coalesced into the Moon: volatiles water, carbon dioxide, nitrogen escaped during the high-temperature phase. Leaving the Moon compositionally depleted relative to Earth, the model explained lunar petrology, orbital mechanics, an Earth-Moon mass ratio while predicting permanent desiccation. Then improved analytical techniques found water in volcanic glass beads and in mineral inclusions within Apollo samples. The concentrations are parts per million rather than parts per billion, suggesting the lunar interior retains water despite surface dryness. Subsequent orbital observations detect hydroxyl absorption features the signature of water molecules or hydroxyl radicals bound to mineral surfaces distributed across lunar highlands and maria. The absorption strengthens at high latitudes and appears correlated with time of day, suggesting solar wind protons strike silicate minerals, react with oxygen in the crystal lattice, and produce hydroxyl groups that migrate or desorb as temperature changes. Water arrives continuously, delivered by impacts and solar wind, not locked in primordial reservoirs. Mars shows water everywhere. The Mars Reconnaissance Orbiter maps recurring slope lineae, dark streaks appearing on crater walls and canyon slopes during Martian summer, fading during winter, repeating annually in the same locations. The streaks are narrow, tens of meters wide, hundreds of meters long, appearing only on sun-facing slopes where temperatures exceed 250 Kelvin. Spectroscopy reveals hydrated salts, perchlorates and chlorates capable of lowering water's freezing point to enable briny liquid flow at temperatures well below 0 Celsius. The interpretation seasonal melting of subsurface ice deposits produces saline water that seeps downslope before refreezing or evaporating. But alternative explanations persist. Granular flow of dry sand can produce similar morphologies if temperature-dependent cohesion controls avalanche initiation. Carbon dioxide frost sublimation can trigger slope failures. Deliquescence atmospheric water vapor condensing directly onto hygroscopic salts can darken surfaces without requiring liquid flow. Each mechanism fits subsets of observations while failing to explain others. Certainty eludes even our nearest neighbours. Europa, Jupiter's fourth largest moon, possesses a global ocean beneath an ice shell 10 to 30 kilometers thick. Tidal heating from orbital resonance with Io and Ganymede flexes Europa's interior, generating enough thermal energy to maintain liquid water despite surface temperatures of 110 Kelvin. Galileo spacecraft detected induced magnetic fields during flybys, indicating electrically conductive material, likely saline water beneath the surface. Surface features include chaotic terrain, double ridges, and bands suggesting ice shell overturn and resurfacing on timescales of tens of millions of years. The ocean contains more liquid water than all of Earth's oceans combined. Enceladus, a small moon of Saturn barely 500 kilometers in diameter, ejects plumes of water vapor and ice particles from fractures near its south pole. The Cassini spacecraft flew through the plumes dozens of times between 2005 and 2017, analysing composition with mass spectrometers. The plumes contain 98% water, 1% molecular hydrogen, traces of methane, carbon dioxide, ammonia, and organic molecules including formaldehyde and methanol. Molecular hydrogen indicates water rock reactions at temperatures above 90 Celsius, suggesting hydrothermal activity on the seafloor of a subsurface ocean. Dry irony. A moon smaller than Texas has active hydrothermal vents. Titan's surface holds liquid methane and ethane in lakes and seas concentrated near the North Polar region. The Cassini radar mapped over 650,000 square kilometres of liquid hydrocarbons, larger than the Caspian Sea. Earth's largest lake, Ligeia Mare, Titan's second largest sea, reaches depths exceeding 160 metres, its composition primarily methane with dissolved nitrogen. The lakes fill and empty on seasonal timescales as Titan orbits Saturn, experiencing methane rainfall and evaporation cycles analogous to Earth's hydrological cycle, but at temperatures of 94 Kelvin, where water is solid as granite and methane is liquid. Every world with a thick atmosphere and volatile substances develops weather. Ceres, the largest object in the asteroid belt, displays bright spots within Okata crater, identified as sodium carbonate deposit salts left behind by briny water that reached the surface and sublimated. Dawn spacecraft observations revealed ammonia-bearing clays, suggesting Ceres formed in the outer solar system beyond Neptune's orbit and migrated inward, carrying ices and organic material from cold outer regions into the warmer inner belt. Transient water vapor emissions detected by Herschel Space Observatory indicate subsurface ice reservoirs occasionally outgas, possibly driven by solar heating or impact-triggered pressure release. Even asteroids retain water, locked away until disturbed. Comets are ice with dust mixed in. Not dust with ice mixed in, a distinction confirmed by Rosetta mission measurements of Comet 67P during 2 years of close observation. The nucleus is porous, with density 470 kilograms per cubic meter, half the density of water ice, implying 50% void space. As the comet approaches the Sun, solar heating sublimates surface ice, releasing dust particles and gas molecules at rates reaching several hundred kilograms per second at perihelion. Water dominates the outgassing, but carbon monoxide, carbon dioxide, methane, ammonia, and molecular nitrogen also appear. The comet's water tastes wrong. Deuterium to hydrogen ratio in 67P's water vapour is 3 times Earth's ocean value, ruling out comets like 67P as the dominant source of terrestrial water. But other comets, particularly those from the Oort cloud rather than the Kuiper belt, show deuterium ratios closer to Earth's, leaving open the possibility that impacts delivered significant fractions of Earth's water inventory during late heavy bombardment 4 billion years ago. Water's origin on Earth remains debated despite water's ubiquity elsewhere. Interstellar clouds contain water ice. Infrared absorption spectroscopy of dense molecular clouds reveals the 3-micron feature of solid water, coating dust grains at temperatures below 100 Kelvin. The ice forms through surface chemistry. Oxygen atoms adsorbed onto dust grains encounter hydrogen atoms, bonding to form hydroxyl and subsequently molecular water through sequential hydrogenation. Protostars forming within these clouds inherit ice-coated grains, delivering water into protoplanetary disks from the earliest stages of stellar system assembly. Water predates planets, stars. Even star-forming regions it accumulates wherever oxygen and hydrogen coexist in sufficient density and low temperature. The discovery pattern repeats: expect dryness, find water, expect rarity, find abundance. The Moon contains water in shadows and possibly in minerals throughout its crust. Mars retains ice at the poles and possibly brines at depth. The outer solar system moons harbour more liquid water than Earth. Asteroids and comets deliver water to inner planets during impacts. The molecule appears in star-forming regions, in protoplanetary disks, in atmospheres of hot Jupiters. Water is common. Earth's oceans become less exceptional with each mission, each spectrum, each detection. Phosphine on Venus appears in millimeter-wave observations conducted in 2017 and 2019, using the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile. The molecule absorbs at 1.123 millimeters wavelength, producing a spectral line at 266.9 gigahertz. Analysis of the absorption strength suggests phosphine concentration near 20 parts per billion at cloud deck altitudes of 50 to 60 kilometers above the surface, where temperatures range from 0 to 60 Celsius and atmospheric pressure equals 1 bar conditions superficially Earth-like, despite the planet's hellish surface environment below. The detection is controversial from announcement. Phosphine consists of one phosphorus atom bonded to 3 hydrogen atoms. On Earth, the molecule is produced industrially or by anaerobic bacteria in swamps, lake sediments, and animal digestive tracts environments where microbes reduce phosphate to phosphine as part of metabolic pathways. Abiotic production occurs during lightning strikes and in circumstellar envelopes of dying stars. But known geological processes on rocky planets do not generate phosphine in detectable quantities. The molecule is thermodynamically unstable in oxidizing atmospheres, destroyed by ultraviolet light and chemical reactions with oxygen, hydroxyl radicals, and sulfuric acid. Its presence on Venus, if real, requires either continuous production to balance rapid destruction or a reservoir releasing stored phosphine gradually. Biology becomes the explanation of a last resort when chemistry fails. But independent analysis of the same data yields different results. Reprocessing the ALMA observations with updated calibration pipelines reduces the detected signal significantly, lowering inferred phosphine abundance from 20 parts per billion to below 5 parts per billion, near or below detection limits. The spectral line appears at frequencies where sulfur dioxide also absorbs, and Venus's atmosphere contains sulfur dioxide at concentrations 3 orders of magnitude higher than the claimed phosphine abundance. Disentangling the two species requires accurate knowledge of line shapes, atmospheric temperature profiles, and instrument systematics. Small errors in any parameter can create false phosphine detections or hide real signals beneath sulfur dioxide contamination. The detection neither confirms nor disappears. Lingering in ambiguity, methane on Mars follows a similar trajectory. Curiosity rover measures methane concentrations in Gale Crater using the tunable laser spectrometer, detecting seasonal variations with background levels near 0.4 parts per billion and occasional spikes reaching 7 parts per billion. The spikes last hours to days before dissipating, suggesting localized release from subsurface reservoirs rather than uniform atmospheric mixing. Methane has atmospheric lifetime of 300 years on Mars due to slow photochemical destruction, so detections imply recent or ongoing production either biological, through methanogenic microbes similar to Earth's subsurface archaea, or geological, through serpentinization reactions where water interacts with iron-rich minerals at elevated temperatures. But the European Space Agency's trace gas orbiter, designed specifically to map Martian methane from orbit, finds no methane above its detection limit of 50 parts per trillion, 10 times more sensitive than Curiosity, but yielding null results. The discrepancy suggests either Curiosity's detections are instrumental artifacts, or methane plumes are too localized and transient for orbital instruments to capture, or both instruments are correct and methane destruction proceeds faster than theory predicts. Consensus awaits instruments that agree. The challenge is abiotic mimicry. Oxygen on Earth accumulates because photosynthesis produces it faster than geology consumes it. But oxygen can also arise from water photolysis, in atmospheres with low hydrogen escape rates or from carbon dioxide photodissociation on planets, orbiting M-dwarfs where ultraviolet flux peaks at wavelengths that break molecular bonds efficiently. Methane on Earth comes primarily from biology, but serpentinization, volcanism, and cometary impacts also release methane without biology. Phosphine, dimethyl sulfide, methyl chloride. Each proposed biosignature has at least one abiotic production pathway that cannot be ruled out without detailed atmospheric context. No single molecule proves life, only combinations suggest it. Atmospheric disequilibrium offers a statistical approach. Earth's atmosphere is far from chemical equilibrium. Oxygen and methane coexist despite reacting on timescales of years, maintained by biological production that outpaces chemical destruction. An exoplanet atmosphere containing oxygen and methane simultaneously, in abundances and ratios inconsistent with known abiotic processes, would warrant further investigation as a potential biosphere indicator. But calculating equilibrium requires knowing atmospheric composition, pressure-temperature profiles, stellar spectrum, surface mineralogy, and volcanic outgassing rates, parameters mostly unconstrained for exoplanets. We search for life using chemistry we barely understand on worlds we cannot visit. False positives accumulate in the literature. Our sign on Venus. Proposed in 2021. Later attributed to instrumental artifacts. Glycine on Comet 67P, initially detected by Rosetta, retracted after improved calibration. Amino acids in Martian meteorite ALH 84001, announced in 1996 as evidence for ancient Martian life, reinterpreted as terrestrial contamination or abiotic synthesis. Each claim follows the same pattern: initial excitement, media coverage, skeptical reanalysis, ambiguous resolution leaving the question open but enthusiasm diminished. Dry irony. We find potential biosignatures everywhere but confirmed life nowhere. The null hypothesis remains strong. No measurement yet obtained conclusively demonstrates biology beyond Earth. Phosphine on Venus may be real or may be sulfur dioxide misidentified. Methane on Mars may exist or may be instrument noise. Each detection sits at margins of instrumental sensitivity. Each interpretation depends on atmospheric models with large uncertainties. Each claim requires independent confirmation that takes years to obtain and often yields contradictory results. Biology is not required by any current observation, though it is permitted by several. The search continues with better instruments. Future missions will directly image rocky exoplanets in habitable zones and obtain medium-resolution spectra capable of detecting oxygen, ozone, water, methane, and other molecules at signal-to-noise ratios sufficient for an ambiguous identification. Technology demonstrations proceed in laboratories. Funding cycles proceed in committees. Launch dates proceed toward the future, contingent on budgets and politics and technological readiness. The biosignatures, if they exist, wait in spectra we have not yet recorded. The Anthropocene begins somewhere between 1750 and 1950, depending on which marker is chosen. The stratigraphic boundary, the physical layer in sediment and ice cores that future geologists might identify as the transition from Holocene to Anthropocene, lacks consensus definition. Proposed markers include the rise in atmospheric carbon dioxide beginning with industrialization, the radioactive fallout from nuclear weapons testing peaking in 1963, the global dispersion of microplastics detectable in sediments worldwide after 1950, or the proliferation of domestic chicken bones in archaeological deposits following intensification of poultry farming. Each marker appears in the geological record as a distinct signal. Each is globally synchronous within dating uncertainties. Each is unprecedented in the prior 11,700 years of Holocene stability. Only took 2 centuries to create a layer visible from orbit and persisting for millions of years. Carbon dioxide concentration measured at Mauna Loa. Observatory rises from 315 parts per million in 1958, when Charles David Keeling begins continuous monitoring, to 426 parts per million in 2025. The Keeling curve shows annual oscillations superimposed on monotonic increased northern hemisphere vegetation, inhales carbon dioxide during spring and summer growing seasons, exhales during autumn and winter as leaves decay and soils respire, creating seasonal variations of 6 parts per million amplitude. But the baseline rises steadily, driven by fossil fuel combustion releasing carbon sequestered underground for hundreds of millions of years. Ice core records extending 800,000 years show natural carbon dioxide variations between 180 and 300 parts per million, never exceeding 300 until the industrial era. The current value is 50% higher than any naturally occurring level in nearly a million years. Plastics enter the stratigraphic record as microparticles less than 5 millimeters diameter, fragments of bottles, bags, fishing nets, synthetic textiles, and industrial pellets degraded by ultraviolet radiation, wave action, and mechanical abrasion. Ocean sediment cores from the Pacific, Atlantic, and Arctic contain microplastic concentrations increasing exponentially after 1950, reaching thousands of particles per kilogram in surface sediments. The particles are polyethylene, polypropylene, polystyrene, polyethylene terephthalate, polymers that do not biodegrade on timescales shorter than centuries. They accumulate in depositional environments, mixing with silt and clay, becoming permanent components of the sedimentary record. Future geologists will find our discarded packaging preserved as fossils. Radionuclide signatures peak sharply. Atmospheric nuclear weapons testing between 1945 and 1980 injects radioactive isotopes into the stratosphere. Cesium, 137 strontium-90 plutonium-239, which disperse globally before settling onto land and ocean surfaces. Ice cores from Greenland and Antarctica show clear spikes in 1963. The year of maximum testing before the Partial Nuclear Test Ban Treaty reduces atmospheric detonations. The isotopes decay predictably. Cesium, 137 has half-life 30.2 years. Strontium-90 has half-life 28.8 years. By 2025, concentrations have declined to approximately 1/4 of peak values, but the fallout remains detectable above pre-industrial background in sediments worldwide. Dry irony, humanity's most destructive technology provides one of its clearest chronological markers. Chicken bones appear in unprecedented abundance. Domestic chickens. Gallus domesticus are the most numerous bird on Earth, with populations exceeding 25 billion individuals at any given time, outnumbering all wild birds combined by a factor of 3. Industrial poultry farming produces chickens with distinctive skeletal morphology, enlarged breastbones to support hypertrophied pectoral muscles, rapid growth rates leaving histological signatures in bone microstructure, and standardized sizes reflecting selective breeding. Archaeological deposits from the late 20th and early 21st centuries contain chicken bones in densities orders of magnitude higher than any prior period. The broiler chicken becomes an index fossil for industrial civilization. Concrete appears in structures and as particulate matter. Annual concrete production exceeds 4 billion tons, roughly half a ton per human per year. The material is calcium silicate hydrate, formed by mixing Portland cement with water and aggregate, creating artificial rock that hardens through hydration reactions. Concrete structures, dams, bridges, buildings, roads erode slowly, releasing particles into rivers and oceans where they mix with natural sediments. The particles are distinguishable from natural limestone by their chemical composition and crystalline structure. Cities leave layers of artificial stone that will puzzle distant future archaeologists. Nitrogen isotope ratios shift in soils and sediments. Industrial fixation of atmospheric nitrogen into ammonia via the Haber-Bosch process supplies synthetic fertilizers applied to agricultural fields at rates exceeding 100 million tons per year. The synthetic nitrogen has isotopic composition slightly different from biologically fixed nitrogen. Depleted in nitrogen-15 relative to nitrogen-14. Runoff carries fertilizer into rivers and coastal zones, where it stimulates algal blooms. The algae incorporate synthetic nitrogen, die, sink, and become buried in sediments. Recording the isotopic shift in organic matter, even the nitrogen cycle carries human fingerprints. Extinction rates accelerate above background. The fossil record documents 5 major mass extinctions over the past 540 million years events, where more than 75% of species disappear within geologically brief intervals. Current extinction rates for mammals, birds and amphibians exceed background rates by factors of 100 to 1,000, driven by habitat loss, overhunting, pollution and climate change. The extinctions do not yet reach mass extinction magnitudes. But projections suggest 20 to 50% of species could face extinction by 2100 under high emission scenarios. The 6th mass extinction assembles in real time, layer by layer, yet the Anthropocene lacks formal ratification. The International Commission on Stratigraphy, which governs geological timescale definitions, requires that new epochs be defined by global boundary stratotype sections and points physical reference sections, where the boundary is exposed and can be sampled. Proposed Anthropocene boundaries remain under debate. Some favour mid-20th century radionuclide spike. Others prefer earlier industrial markers or later plastic proliferation. The decision involves not only scientific criteria, but also political and philosophical dimensions. Declaring a new epoch announces that human activity has become a geological force. Geology moves slowly, even when recording rapid change. The layer accumulates regardless of nomenclature. Sediments deposited in 2025 contain plastics, radionuclides, altered nitrogen isotopes, concrete particles, and fossil fuel combustion residues. The layer is thin centimetres thick in most depositional environments, but globally extensive and geochemically distinct from underlying Holocene sediments. Future geologists, if they exist, will identify this boundary easily, whether or not we name it. The Anthropocene is less a formal epoch than a confession written in sediment. Solar storms begin at the sun's surface, where magnetic field lines twisted by differential rotation, the equator spinning faster than the poles, store energy in coronal loops rising thousands of kilometres above the photosphere. The loops are visible during total solar eclipses as bright arcs and streamers extending into space, their shapes tracing magnetic field geometry. When field lines reconnect, releasing stored magnetic energy, the result is a solar flare, a sudden brightening in X-ray and ultraviolet wavelengths, accompanied by acceleration of charged particles to near relativistic speeds. The flare photons travel at light speed, reaching Earth in 8.3 minutes. The particles follow slightly later, arriving in tens of minutes to hours depending on their energies and the magnetic field configuration between Sun and Earth. No warning precedes the photons. They arrive simultaneously with observation. Coronal mass ejections follow different trajectories. These events expel billions of tons of magnetized plasma from the solar corona into interplanetary space, forming clouds that expand as they propagate outward at speeds ranging from 200 to 3,000 kilometers per second. Fast coronal mass ejections reach Earth in 15 to 18 hours. Slow ones take 2 to 4 days. The plasma carries embedded magnetic field with orientation determined by the source region on the Sun. If the field points southward upon arrival at Earth opposite to Earth's northward pointing magnetic field, reconnection occurs at the magnetopause, allowing solar plasma to enter the magnetosphere and trigger geomagnetic storms. Field orientation cannot be measured until the cloud arrives at spacecraft positioned between Sun and Earth. The Advanced Composition Explorer satellite orbits the L1 Lagrange point, 1,500,000 kilometers sunward of Earth, monitoring solar wind conditions in real time. When a coronal mass ejection passes the spacecraft, Instruments measure plasma density, velocity, temperature, and magnetic field vector, transmitting data to ground stations within seconds. The measurements provide advance warning of geomagnetic storm onset approximately 30 to 60 minutes before the disturbance reaches Earth's magnetosphere. 30 minutes is sufficient to issue alerts to power grid operators, satellite operators, and aviation authorities. It is insufficient for many mitigation measures that require hours to implement. Dry irony. We can predict hurricanes days in advance, but solar storms only after they arrive. Geomagnetic storms induce currents in long conductors. Power transmission lines extending hundreds of kilometers act as antennas for time-varying magnetic fields, generating voltages that drive geomagnetically induced currents through transformer windings and into the ground. The currents are quasi-DC, flowing at frequencies below 1 Hz, saturating transformer cores and causing them to draw excessive reactive power, overheat, and potentially fail. Transformers are custom-built, requiring months to years to manufacture and replace. Loss of multiple transformers simultaneously could leave regions without power for extended periods. The Carrington event of 1859 provides historical reference. Telegraph systems across Europe and North America experienced disruptions, with operators reporting sparks leaping from equipment and some lines continuing to operate without battery power, driven entirely by geomagnetically induced currents. Auroras appeared at tropical latitudes, visible from Cuba and Hawaii. The event occurred during solar maximum, but its intensity exceeded typical solar cycle variations. Modern estimates suggest the associated coronal mass ejection travelled at speeds near 2,000 km per second, carrying magnetic field strengths an order of magnitude stronger than typical storms. If a Carrington-class event occurred today, impacts would extend beyond power grids. High-frequency radio communications would degrade or fail due to ionospheric disturbances. GPS positioning errors would increase as ionospheric delays corrupt signal propagation times. Satellite operations would face enhanced drag from atmospheric expansion and increased radiation exposure from energetic particles trapped in the magnetosphere. Yet prediction remains elusive beyond the 30-minute warning window. Solar flare forecasting relies on observations of active regions, concentrations of strong magnetic field visible as sunspots on the solar disk. Satellites monitor these regions continuously, measuring magnetic field strength, complexity, and evolution. Certain configurations, large sunspot groups with mixed magnetic polarity, regions showing rapid flux emergence or shear correlate with increased flare probability. Statistical models assign probabilities a given active region has 10% chance of producing an X-class flare within 24 hours. But the models cannot predict exact timing or whether an eruption will occur at all. Flares happen when magnetic fields reconnect, and reconnection triggers remain poorly understood. Coronal mass ejection prediction is even more uncertain. Not all flares produce coronal mass ejections, and some coronal mass ejections occur without associated flares. The relationship between surface magnetic field observations and coronal mass ejection initiation is indirect, mediated by complex dynamics in the corona where plasma pressure, magnetic tension, and gravitational forces interact. Models simulate these interactions using magnetohydrodynamics, solving coupled equations for plasma motion and magnetic field evolution. The simulations reproduce observed eruptions in retrospect but struggle to predict future events. Only after an eruption begins can its trajectory and speed be estimated, and only roughly. Space weather forecasting resembles terrestrial weather. Forecasting from the 1950s, observations are sparse, models are crude, predictions are statistical rather than deterministic. Solar Dynamics Observatory provides high-cadence full-disk images in multiple wavelengths, updating every 12 seconds, but cannot observe the far side of the Sun where active regions develop before rotating into Earth view. A comprehensive monitoring system would require multiple spacecraft distributed around the Sun, continuously observing the entire solar surface, a constellation that does not yet exist. The Sun rotates every 27 days. Active regions on the far side remain invisible for 2 weeks. Mitigation strategies exist but are incompletely implemented. Power grids can be reconfigured to reduce geomagnetically induced current flow by opening certain switches and isolating vulnerable transformers. Satellite operators can place spacecraft in safe modes. Airlines can reroute polar flights to lower latitudes. Each measure has costs: economic, operational, logistical. Implementing them requires advance notice measured in hours to days, but current warning times are measured in minutes to hours. The gap between what is needed and what is available defines vulnerability. The storms continue regardless of preparedness. Magnetic fields on the Sun twist and reconnect according to plasma physics laws indifferent to human infrastructure. Coronal mass ejections propagate through interplanetary space whether or not spacecraft monitor their passage. Earth's magnetosphere responds to solar wind, forcing whether or not operators stand ready. 8 minutes for light, 30 minutes for warning, hours for arrival. The Sun remains faster. Near-Earth objects are asteroids and comets whose orbits bring them within 1.3 astronomical units of the Sun, close enough to intersect Earth's orbit during some portion of their trajectory. The population includes approximately 25,000 known objects larger than 140 meters diameter, discovered through systematic sky surveys that image the same regions repeatedly, searching for moving points of light against the fixed star background. Detection rates have accelerated: 500 objects discovered annually in the early 2000s, 2,000 per year by 2010, over 3,000 per year by 2020. The catalogue grows but remains incomplete. Completeness estimates depend on object size. For asteroids larger than 1 kilometer impactors capable of global catastrophic effects, surveys have identified approximately 95% of the population, totaling about 1,000 objects. None currently pose impact threat within the next century based on orbit calculations. For objects between 140 meters and 1 kilometer city destroyers rather than civilization enders, completeness drops to approximately 40%. Thousands remain undiscovered, their orbits unknown, their future positions uncalculable. Only the largest threats are catalogued. Medium threats remain mostly invisible. Orbit determination requires multiple observations separated by weeks to months. A single detection provides position and apparent motion, but cannot uniquely determine the full three-dimensional orbit. Observations from different nights constrain the orbital element's semi-major axis, eccentricity, inclination, and angular parameters through least squares fitting of predicted positions to observed positions. Uncertainty decreases with observation. Arc length an object observed over 1 week has position uncertainty of thousands of kilometers a century hence. The same object observed over 1 year has position uncertainty reduced to hundreds of kilometers. For objects passing near Earth, radar observations provide precise range and velocity measurements. Shrinking uncertainty ellipsoids dramatically. Some objects remain uncertain despite decades of tracking. Asteroid Bennu, target of the OSIRIS-REx sample return mission, has impact probability of 1 in 2,700 for the year 2182. The uncertainty arises from the Yarkovsky effect. Anisotropic thermal emission from a rotating asteroid creates tiny thrust, altering the orbit over decades. The effect depends on asteroid size, shape, rotation rate, thermal properties, and surface composition. For Bennu, the Yarkovsky acceleration amounts to a few hundred nanometers per second squared, negligible over short timescales but accumulating to orbit changes of hundreds of kilometers over a century. A 1 in 2,700 chance over the next century and a half becomes neither alarming nor dismissible. Apophis provides another example. discovered in 2004. Initial orbit calculations showed small but non-zero impact probability for 2029 high enough to briefly reach level 4 on the Torino scale, indicating close encounter with regional devastation potential. Subsequent observations refined the orbit, eliminating the 2029 risk. A close approach will occur in 2029. The asteroid will pass 32,000 kilometers from Earth's surface, closer than geostationary satellites, but will not impact. The encounter will slightly alter Apophis's orbit through Earth's gravitational perturbation, changing future trajectories in ways that depend sensitively on the exact approach geometry. Gravitational keyhole effects complicate long-term predictions. If an asteroid passes through a specific small region during one close approach, Earth's gravity bends the trajectory just enough to guarantee impact during a subsequent approach years or decades later. The keyholes are narrow, typically tens to hundreds of meters wide in space, but crossing one converts a miss into a future certainty. Determining whether an asteroid will thread a keyhole requires knowing its position to better than the keyhole width at the time of passage. Dry irony, asteroids are discovered, tracked, and calculated. But the final 5% uncertainty persists. Deflection strategies exist in theory. Kinetic Impactor's spacecraft crashed into asteroids at high velocity transfer momentum, changing orbital velocity by millimeters per second. The Double Asteroid Redirection Test, DART, demonstrated this technique in 2022 by impacting Dimorphos, a moon of asteroid Didymos, shortening its orbital period by 33 minutes. The momentum transfer efficiency exceeded predictions by a factor of 3 due to ejected debris carrying additional momentum. Scaling to larger asteroids and longer deflection timescales suggests that years to decades of warning time enable successful deflection with current technology. But deflection requires early detection, accurate orbit prediction, and political will to act on probabilistic threats. Gravity tractors provide gentler deflection. A spacecraft hovering near an asteroid for months to years exerts tiny gravitational pull, slowly altering the asteroid's velocity without contact or impact. The method requires no knowledge of asteroid composition or structural strength and produces predictable deflection. But thrust levels are minuscule nanometers per second squared, requiring years of operation to accumulate meaningful orbit changes. Nuclear standoff bursts offer high-energy alternatives. A nuclear device detonated tens to hundreds of meters from an asteroid's surface vaporizes surface material, creating an expanding plume that imparts momentum through ablation pressure. The method works for large asteroids where kinetic impactors provide insufficient momentum transfer, but nuclear options carry political complications and require extensive testing to validate models of energy coupling and ablation physics. No deflection mission has yet been attempted against an object threatening Earth, because no such object is currently known. The impact hazard is statistical rather than imminent. Objects larger than 1 kilometer strike Earth approximately once per million years on average. Objects in the 140-meter range impact once per few thousand years. Smaller objects, tens of meters diameter, enter the atmosphere every few decades, but typically explode at a high altitude. The Chelyabinsk meteor of 2013, a 20-meter object, released energy equivalent to 500 kilotons of TNT at an altitude of 30 kilometers, shattering windows and injuring over 1,000 people through indirect blast effects. Statistical hazards challenge risk perception and policy response. A 1 in 10,000 per year probability of regional destruction is high enough to warrant mitigation investment, but low enough that most decision-makers experience no impacts during their lifetimes. Funding for surveys and deflection technology development competes with immediate needs whose benefits are certain and tangible. We build catalogues, refine orbits, and practice deflection on asteroids that pose no threat, preparing for the object we have not yet found. The sky surveys continue. New telescopes come online, pushing completeness toward 90% for objects above 140 meters. Space-based infrared surveys will find dark asteroids invisible to optical telescopes. International coordination improves, with data sharing and orbit computation distributed across multiple centers. The catalogue grows toward completeness, but completeness asymptotes below 100%. Small dark objects on eccentric orbits remain findable only during brief intervals when they approach Earth. Long-period comets from the Oort cloud provide minimal warning due to their extreme distances and faintness until they enter the inner solar system. The catalogue improves. The uncertainty shrinks but does not vanish. 5% remains unfound. Climate models are systems of coupled differential equations representing energy, mass and momentum conservation across atmosphere, ocean, land surface, and cryosphere. The atmosphere is discretized into grid cells typically 100 kilometers horizontal resolution, 30 to 60 vertical levels within which temperature, pressure, humidity, wind velocity, and cloud properties are calculated at time steps of minutes to hours. Ocean models use similar discretization, though with finer vertical resolution near the surface where gradients are steep. Land surface models track soil moisture, vegetation state, snow cover, and surface energy balance. Ice sheet models simulate glacier flow, calving, and mass balance. The components exchange fluxes across their boundaries every simulated time step. The equations are known. The solutions are not, except through numerical approximation. Model validation proceeds through hindcasting. Historical simulations beginning in 1850 reproduce observed global temperature increase of approximately 1.2 degrees Celsius between pre-industrial baseline and 2020. The models capture the mid-century warming pause when aerosol emissions from fossil fuel combustion temporarily offset greenhouse gas forcing. They reproduce regional patterns Arctic amplification with warming proceeding twice as fast at high northern latitudes, land warming faster than ocean, nighttime minimum temperatures rising faster than daytime maxima. The agreement is imperfect models systematically underestimate Arctic sea ice decline, but correlation between simulated and observed temperature fields exceeds 0.9 globally. Agreement on past climate does not guarantee accuracy for future climate, but it provides necessary if insufficient validation. Projections depend on emission scenarios. The sixth assessment report of the Intergovernmental Panel on Climate Change presents 5 shared socio-economic pathways spanning from rapid decarbonisation with net zero emissions by 2050 to continued fossil fuel dominance with emissions doubling by 2100. Each pathway feeds into climate models as prescribed greenhouse gas concentrations or emissions rates. Ensemble simulations, 30 to 50 models run by institutions worldwide, produce probability distributions for future temperature, precipitation, sea level, and other variables. The ensemble mean for the middle-of-the-road scenario projects warming of 2.7 degrees Celsius by 2100 relative to pre-industrial. The range across models is 1.8 to 3.6 degrees. The error bars never quite disappear, even as models improve. Regional projections carry larger uncertainties than global projections. While models agree on global temperature trends to within 20%, regional precipitation changes vary by factors of 2 or more across ensemble members. Mediterranean region shows drying in most models but wetting in a few. East African monsoon strengthens in some simulations, weakens in others. The disagreement traces to different representations of convection, cloud feedbacks, and land-atmosphere coupling processes occurring at scales smaller than model grid cells, parameterized rather than explicitly resolved. Parameterizations are necessary approximations, equations relating subgrid processes to resolved variables through empirical relationships. Cloud feedbacks dominate uncertainty and climate sensitivity, the equilibrium temperature change resulting from doubling carbon dioxide concentration. Low clouds cool the planet by reflecting sunlight. High clouds warm the planet by trapping outgoing infrared radiation. As climate warms, cloud properties change, cloud top heights shift. Liquid water content adjusts, cloud fraction increases or decreases depending on region and season. Different models produce different cloud responses, leading to climate sensitivities ranging from 2.5 to 5 degrees Celsius for doubled carbon dioxide, a factor of 2 spread persisting across model generations. Observations constrain some feedbacks, but not enough to collapse the range significantly. Ocean heat uptake determines transient warming rates. The ocean absorbs over 90% of excess heat trapped by increased greenhouse gases, with most warming concentrated in the upper 2,000 metres. Deep ocean warms slowly, requiring centuries to millennia to equilibrate with surface forcing. Models with vigorous deep mixing sequester heat efficiently, producing lower surface warming on century timescales. Models with sluggish mixing retain heat near the surface, producing faster warming. Observational constraints from Argo float profiles, satellite altimetry, and hydrographic surveys limit but do not eliminate intermodal spread in ocean heat uptake. The ocean is warming. The rate remains uncertain within 30% bounds. Ice sheet dynamics introduce further uncertainty, particularly for sea level projections. Greenland ice sheet mass loss accelerates approximately 50 gigatons per year in the 1990s, 250 gigatons per year in the 2010s, driven by increased surface melting and accelerated glacier discharge. Antarctic ice sheet shows regional contrasts. West Antarctic glaciers thin and retreat. East Antarctic interior thickens from increased snowfall. Marine ice sheet instability threatens substantial contribution to sea level rise if triggered. Models incorporating ice dynamics project sea level rise of 0.4 to 1.3 meters by 2100 under moderate emission scenarios. The range reflects uncertainty in ice sheet response to warming. Some models predict gradual melting. Others predict threshold crossing followed by rapid collapse. Paleoclimate evidence from past warm periods suggests polar ice sheets can collapse on millennial timescales. But whether such collapses can be triggered within centuries remains contested. Dry irony: we measure ice loss to the gigaton but predict future loss with 60% error bars. Model intercomparisons reveal systematic biases. Most models simulate tropical Pacific sea surface temperatures warmer than observed, affecting El Niño frequency and teleconnections. Some models produce excessive rainfall over tropical land, others underestimate monsoon strength. High-latitude cloud cover is overestimated in winter, underestimated in summer. These biases do not necessarily invalidate projections. A model can simulate future changes correctly despite biased mean state, if the response to forcing is accurate, but they reduce confidence in regional details. Tipping points represent non-linear regime shifts. Atlantic meridional overturning circulation transports heat northward, warming Europe and influencing global climate. Fresh water input from Greenland melting can weaken the overturning by reducing surface water density. Some models show gradual weakening. Others show abrupt collapse if freshwater input exceeds critical threshold. Collapse would cool North Atlantic region, shift tropical rainfall bands, and alter global temperature patterns, but precise threshold location and reversibility remain unknown. Amazon rainforest dieback, permafrost carbon release, coral reef collapse. Each potential tipping element carries large uncertainties in threshold, timescale, and impact magnitude. Despite uncertainties, projections converge on uncomfortable ranges. All emission scenarios except the most aggressive mitigation exceed Paris Agreement targets of limiting warming to 1.5 degrees Celsius. Even with net zero emissions by mid-century, committed warming from historical emissions likely pushes temperatures above 1.5 degrees temporarily. Exceeding 2 degrees is avoided only under pathways requiring rapid transformation of energy systems. The physics is certain more greenhouse gases mean warmer climate. The question is how much warmer, how fast, and with what regional details. Model ensembles provide probabilistic answers, likely ranges, confidence intervals, statements about statistical likelihood rather than deterministic certainty. The sixth assessment report expresses findings with calibrated language. Virtually certain means 99% probability. Very likely means 90%. Likely means 66%. Statements are probabilistic, uncertainties are quantified, and the range is narrow with each assessment cycle. But uncertainty is irreducible, not ignorance. The climate system is chaotic, clouds are complex, and the future depends on human choices not yet made. The peer review process begins when a manuscript is submitted to a journal. The editor, typically a practicing scientist in the relevant field, performs initial screening, rejecting papers that are obviously flawed, outside the journal's scope, or inappropriate for the target audience. Papers passing initial screening are assigned to reviewers, usually 2 to 4 experts selected based on publication records, institutional affiliations, and subject matter expertise. The reviewers receive the manuscript anonymously or with author names visible. Depending on whether the journal employs single-blind, double-blind, or open review, they're asked to evaluate scientific validity, methodological rigor, novelty, significance, and clarity of presentation. The process takes weeks to months, unpaid, conducted as professional service. Reviewers return comments categorized as major revisions, minor revisions, or rejection. Major revisions require substantial additional experiments, reanalysis or rewriting before the paper can be reconsidered. Minor revisions address clarity, completeness, or interpretation without requiring new data. Rejection terminates consideration at that journal, though authors typically submit elsewhere, beginning the cycle again. The editor synthesizes reviewer comments, adds their own assessment, and returns a decision to the authors. Acceptance without revision is rare. Most papers undergo at least one revision cycle. Many undergo 2 or 3. Only a fraction of submitted papers appear in print unchanged from initial submission. Independent replication provides stronger validation than peer review. A result accepted for publication has passed editorial scrutiny but may still contain errors, statistical artifacts, or findings that do not generalize beyond specific conditions. Replication attempts conducting the same experiment or analysis using independent data, different equipment, or alternative methods test whether results are reproducible. Successful replication increases confidence. Failed replication raises questions: was the original finding spurious? Or do subtle methodological differences explain the discrepancy? The replication rate varies dramatically by field, with psychology and social sciences showing lower rates than physics or chemistry. Pharmaceutical research requires regulatory replication. A drug candidate showing efficacy in phase 2 trials must demonstrate similar efficacy in phase 3 trials involving different patient populations conducted at different institutions. Before approval, the trials are expensive, hundreds of millions of dollars, and many candidates fail at this stage, unable to reproduce earlier promising results. The stringency reflects stakes. Failed drugs cause harm, financial loss, and erosion of public trust. The same stringency does not apply in basic research, where negative results are less likely to be published and replication attempts are rare. Incentives favor novelty over replication, discovery over verification. Meta-analysis aggregates results across multiple studies, weighting each by sample size, effect size, and methodological quality. The approach is common in medicine and ecology, where individual studies are small and variable, but collective evidence from dozens of studies can support robust conclusions. Meta-analysis of climate sensitivity estimates combines evidence from instrumental records, paleoclimate proxies, model simulations, and process studies, yielding probability distributions narrower than any single line of evidence provides. But meta-analysis assumes studies are independent, publication bias is absent, and heterogeneity among studies reflects random variation. These assumptions are rarely fully satisfied. Publication bias skews the literature toward positive findings. Statistically significant results are more likely to be written up, submitted, and accepted than null results or negative findings. The bias is strongest in fields where experiments are inexpensive and many research groups investigate similar questions. Estimating the magnitude of publication bias is difficult because unpublished studies are invisible. Though methods exist, funnel plots detect asymmetry in effect sizes versus sample sizes, suggesting small studies with non-significant results are missing. Some journals now accept registered reports peer review of protocols before data collection, with commitment to publish regardless of results. But most journals still prioritize surprising positive findings over expected null results. Retraction rates have increased, driven partly by improved detection of misconduct and partly by actual increases in problematic research practices. Image manipulation, data fabrication, plagiarism, and authorship disputes lead to retractions, which are indexed publicly and damage researcher reputations. Some retractions result from honest error miscalibrated instruments, software bugs, misidentified samples. Distinguishing honest error from misconduct is often impossible from published records alone. Retraction rates remain below 1% of published papers. Though this likely underestimates the true rate of flawed research, dry irony, the scientific literature is self-correcting, eventually, incompletely. Preprints circumvent traditional peer review by allowing immediate public dissemination. Arxiv, Biorexiv, and similar servers host manuscripts prior to journal submission, making results available months before formal publication. The practice accelerated during COVID-19 pandemic when rapid information sharing was prioritized over thorough vetting. Preprints enable fast dissemination but also propagate errors, as demonstrated by numerous retracted or heavily criticized preprints that received media attention before peer review identified fatal flaws. The line between preliminary and published blurs in the preprint era. Consensus emerges slowly through accumulation of corroborating evidence. A single paper claiming extraordinary results faster than light neutrinos. Room temperature superconductors. Life in Martian meteorites is treated skeptically until independent groups reproduce findings. Most extraordinary claims evaporate upon closer examination. The faster-than-light neutrinos resulted from loose fiber optic cable affecting timing measurements. Room temperature superconductor claims have repeatedly failed replication. Martian meteorite biosignatures remain controversial with abiotic explanations available. Extraordinary claims require extraordinary evidence, and evidence accumulates at the pace of experiments, not headlines. Scientific consensus is not unanimous agreement but convergence of independent lines of evidence assessed by expert communities. Anthropogenic climate change is consensus. Multiple datasets show warming. Multiple attribution studies isolate greenhouse gas forcing as the dominant cause. Physical understanding from radiative transfer theory provides mechanism. Dissenters exist, but a few. The arguments have been examined and found wanting, and no alternative explanation accounts for the full range of observations. Consensus on evolution, heliocentrism, germ theory. Plate tectonics followed similar trajectories. Initial controversy, accumulation of evidence, eventual overwhelming acceptance. Yet consensus can be wrong. Continental drift was rejected by most geologists until 1960s, when seafloor spreading and paleomagnetic evidence forced reconsideration. Ulcers were attributed to stress and diet until 1980s, when Barry Marshall and Robin Warren demonstrated bacterial cause. Consensus represents the best current understanding given available evidence, not eternal truth. It shifts when new evidence warrants But shifts require substantial justification, because the bar for overturning established understanding is high. The mechanism is conservative by design, resisting change until change is compelled by data. Cross-validation strengthens confidence. When different measurement techniques, ground stations, satellites, buoys, autonomous floats all show ocean warming, the consistency argues against instrument artifacts. When multiple climate models project warming under increased greenhouse gases, the agreement suggests robust physical understanding. When paleoclimate proxies independently reconstruct past temperatures and all show coherent patterns, the convergence validates proxy methods. Triangulation through independent methods is more convincing than any single measurement chain, however precise. The process is slow, messy, sometimes corrupt, frequently inefficient, yet productive over time. Errors are published, retracted, or quietly abandoned as contrary evidence accumulates. Promising findings fail to replicate and are forgotten. Controversial results are tested, confirmed or refuted, integrated or discarded. The literature grows by millions of papers per year, most incremental, some wrong, a few transformative. Consensus is the sum of imperfect studies judged by imperfect reviewers, debated at imperfect conferences, and tested against imperfect data. It works better than any alternative yet devised for generating reliable knowledge about the natural world. The telescope points outward into darkness, collecting photons that have travelled for billions of years across expanding space. Each observation is a question posed to the universe: what elements compose that star? How fast does that galaxy recede? Does that planet harbour water vapour in its atmosphere? The answers arrive as electromagnetic radiation, visible light, infrared heat, radio waves, X-rays, each wavelength carrying information encoded in intensity, spectrum, polarization, and time variability. Instruments decode the signals, spectrographs disperse light into constituent wavelengths. Photometers count photons. Interferometers combine signals from multiple collectors to achieve resolution finer than any single mirror provides. The universe responds in the language of physics, indifferent to whether anyone listens. The microscope points inward toward complexity, resolving structures invisible to unaided eyes. Cells divide, proteins fold, neurons fire, molecules assemble and disassemble in solutions. Electron microscopes achieve resolution below 1 nanometer, revealing individual atoms arranged in crystal lattices or biological macromolecules. Scanning probe microscopes trace surface topography with tips narrow as single atoms, mapping electronic states, magnetic domains, and mechanical properties at scales where classical and quantum descriptions merge. Cryoelectron microscopy freezes biological samples in vitreous ice, preserving native structure while avoiding damage from crystallization, enabling three-dimensional reconstruction of protein complexes from thousands of projection images. Matter reveals itself when examined with sufficient care and appropriate tools. Between telescope and microscope lie all scales of observation satellites monitoring Earth's atmosphere and oceans, seismometers recording elastic waves propagating through the planet's interior, particle colliders producing exotic states of matter that existed only in the early universe. Each instrument extends human perception beyond the narrow band of directly accessible phenomena, the range of wavelengths visible to eyes, the range of forces perceptible to touch, the range of timescales apprehensible to consciousness. Science becomes possible when tools overcome biological limitations, making the too distant, too small, too fast, or too slow accessible to measurement. Observation is mediated, always, through chains of transduction converting physical signals into numbers in databases. Error bars quantify uncertainty. A measurement reported as 4.2 plus or minus 0.3 acknowledges that the true value lies somewhere in the range 3.9 to 4.5 with specified probability, typically 68% for 1 sigma error bars. 95% for 2 sigma. The uncertainty combines statistical errors from counting photons or sampling populations and systematic errors from instrument calibration, environmental conditions, and analysis choices. Reducing statistical error requires more observations. Reducing systematic error requires better understanding of measurement process, independent calibration, and cross-checks with alternative methods. Precision is the repeatability of measurements. Accuracy is their correctness. Instruments can be precise but inaccurate if systematic biases remain undetected. Null results carry information equal to positive detections. Dark matter searches returning no signal after decades of observation constrain the parameter space of possible dark matter properties, ruling out entire classes of models. Gravitational wave detectors operated for years before the first detection. Each year of null results providing upper limits on merger rates and testing instrument sensitivity. Searches for proton decay have found no events despite monitoring thousands of tons of material for decades, setting lower limits on proton lifetime exceeding 10 to the 34 years longer than the age of the universe by 24 orders of magnitude. Absence of evidence is evidence of absence when experiments have sufficient sensitivity to detect the phenomenon if present. Calibration chains trace measurements back to fundamental standards. The meter is defined as the distance light travels in vacuum during 299,792,458 of a second. The second is defined by 9,192,631,770 periods of radiation, corresponding to the transition between 2 hyperfine levels of cesium-133 ground state. Mass is defined by fixing Planck's constant to exact value 6.62607015 times 10 to the minus 34 joule seconds. Other units derive from these through equations of physics. Standards are conventions, but conventions disciplined by physics and maintained with nanoscale precision. Archives preserve data beyond the lifetimes of instruments and investigators. The Hubble Space Telescope archive contains over 170 petabytes accumulated since 1990, available for reanalysis as new techniques develop or new questions arise. Discoveries are made in archival data years or decades after original observations, exoplanets found by reanalyzing old images, transient events identified in survey data, systematic trends revealed by combining datasets that were never intended to be compared. The archives are collective memory, growing faster than any individual can process, requiring automated pipelines and machine learning algorithms to extract information from data volumes exceeding human capacity for direct examination. Data outlive theories. Observations remain valid when interpretations change, yet observations are theory-laden. Deciding where to point a telescope requires assumptions about which objects are interesting. Designing an instrument requires models of what signals to expect. Interpreting measurements requires frameworks relating detector outputs to physical quantities. The boundary between observation and interpretation is not sharp. Reporting the detection of oxygen in an exoplanet atmosphere already incorporates spectroscopic theory, radiative transfer models, and assumptions about atmospheric structure. The raw data are photon counts. The scientific claim is an inference requiring substantial theoretical scaffolding. No observation is purely empirical, and no theory is purely theoretical. Knowledge emerges from their entanglement. The instruments will improve. Telescopes will grow larger mirrors, achieving deeper sensitivity and finer resolution. Detectors will reach lower noise floors, counting individual photons with higher efficiency and timing precision. Microscopes will probe faster timescales and colder temperatures, approaching limits set by uncertainty principle and thermal fluctuations. Computers will process data faster, simulating larger systems with better accuracy. Each improvement enables questions that were previously unanswerable: galaxies too faint, molecules too transient, processes too complex, but limits remain. Quantum mechanics forbids perfect measurement. Thermodynamics constrains information density. Light speed limits how far we can see into the past or exchange signals with distant probes. Computational complexity restricts which systems can be simulated. Funding and human attention are finite resources, forcing choices about which questions to pursue and which instruments to build. Science proceeds at the intersection of physical possibility, technological capability, and social priority. The universe is larger than our instruments. Complexity exceeds our models. Questions multiply faster than answers. Stillness settles over observatories as dawn approaches. Telescope domes close, sealing mirrors against dust and thermal gradients. Detectors power down, their nightly accumulation of photons complete. Data files compress and transfer to archive servers, joining petabytes of previous observations awaiting analysis. The stars continue shining, galaxies continue rotating, planets continue orbiting. Regardless of whether any instrument watches, the universe proceeds according to its regularities. Unobserved portions evolving in parallel with observed portions. The overwhelming majority of cosmic events occurring beyond any possibility of detection. Observations sample the universe. They do not exhaust it. Researchers sleep or do not sleep, thinking about anomalies in the data, patterns not yet understood, models that fit some observations but fail others. Tomorrow brings new observations, new analysis, new papers to write and read and critique. The process continues incremental, patient, occasionally interrupted by discoveries that reframe entire fields, but mostly accumulating through small steps. Careful measurements, rigorous error analysis, and honest reporting of what is known, what is uncertain, and what remains unknown. The worst theories grow with each new image because the best theories are always provisional, improved by data that reveals their inadequacies, refined through confrontation with observations that refuse to conform to expectations. Science is not a collection of facts, but a process of measurement, a dialogue between instruments and nature, a conversation conducted in the language of calibrated uncertainty. The telescope points outward, the microscope points inward. Both record signals from domains where human intuition fails and direct experience misleads. The measurements accumulate in databases, organized by wavelength and coordinate, tagged with error bars and instrument identifiers, available for retrieval, reanalysis, and reinterpretation by anyone with access and interest. Knowledge is what remains after hypotheses have been tested, theories have been challenged, and measurements have been independently verified. It is partial, uncertain, subject to revision, but earned through effort and validated through replication. It is the best account we have of how things are, pending better observations and deeper understanding. The observations end where instruments end. Beyond detector sensitivity lies unknown territory, dark matter that leaves no trace except gravitational. Distant galaxies too faint for current telescopes. Quantum states that decohere before measurement. Historical events that left no records. The known fades into the unknown without sharp boundary, and the unknown stretches infinitely in all directions. Instruments rest, archives fill, the universe continues, mostly unobserved, its photons propagating through vacuum toward detectors that may or may not exist when they finally arrive after journeys spanning cosmic ages. Sleep arrives like cosmic background radiation everywhere, ancient, cooling, carrying information from earlier times now stretched and redshifted into whispers barely distinguishable from silence.